Greetings, judges. We are 22NUSH13, and today we will be presenting on our SMP project titled Ab Initio Calculation of Electronic Structure, Magnetism, and Derivation of Ligand Field Parameters for 5D4 Transition Metal Compounds. First, we will cover the introduction, followed by the computational methods we used, and then the results and discussion, followed by a brief conclusion of the project. First, the introduction. What is the role of 5D transition metals in society? They are important catalysts since their partially filled d orbitals can easily help to withdraw or accept electrons from reagents, providing alternative reaction pathways to lower activation energies of reactions. They can also act as impurities in crystals, as they can induce optical properties in crystals and modulate the band gaps of the crystals. When the atom is hit by a photon, it will absorb wavelengths of visible light, and thus they can be used in the industry as dyes. Hence, it is important to analyze the properties of transition metals and necessary to derive a quantitative model to accurately predict its properties.
Computational chemistry aims to use computational methods to calculate properties of molecules. The Hartree-Fock method calculates properties by using only one such expression that describes the wave function of the molecule, called a Slater determinant. However, the true wave function requires many more Slater determinants, and thus this only achieves about 90% accuracy. On the other end of the spectrum, there is the fully accurate full wave function, which takes into account all orbitals from the basis set and all possible Slater determinants, achieving the true theoretical result at the cost of extreme computing power. This can be done for very small particles, but is certainly not feasible with large particles, such as the 5D transition metals in our projects. Therefore, most computational chemistry falls within these two domains, achieving higher accuracy than Hartree-Fock and optimizing lower energies while requiring more computational resources.
Now, we shall talk about some basic concepts of our project. In a free ion, all the 5D orbitals are degenerate, and since there are no external perturbations to them. However, in a crystal environment, the 5D orbitals split in energy due to the electrostatic perturbation caused by negative charges of the ligands, as well as by covalence between the ligand and metal orbitals. For example, in octahedral symmetry, the 5D orbitals are split in two groups, the T2G, which is lower in energy, and EG, which is higher in energy. Furthermore, due to the Jahn-Teller effect, geometric distortion of the octahedral complex reduces its symmetry and lowers its energy. This leads to the breaking of degeneracy of the T2G and EG orbitals. However, we notice that the axial perturbation is the dominant one, and therefore we may model this splitting using a simple model Hamiltonian. This model Hamiltonian employs four ligand field parameters, which will be described in more detail later on.
One of the goals of this project is to investigate the low-lying energy structure and magnetism of two rhenium-3 molecules and give a simple ligand field interpretation of the low-lying energy states by employing a model Hamiltonian for this purpose. Two molecules used are rhenium hexachloride, which is the model compound, and ReCl3-TPPZ. We will refer to ReCl3-TPPZ as the rhenium-3 molecule from now on. All experimental data of the rhenium-3 molecule was obtained from the study conducted by Palion Garza in 2015. Meanwhile, we will also obtain the vibrational frequencies, Io spectra, electronic density, and energy by using computational methods.
Using computational methods, we can obtain the ab initio values of the two molecules. We then construct the model Hamiltonian according to this equation, and diagonalization of the Hamiltonian provides us with 9 values in terms of 4 ligand field parameters. Fitting the ab initio values into the diagonalized Hamiltonian, we can obtain the ligand field parameters, lambda, delta, epsilon, and kappa.
Now, we will talk about the computational methods used in this project. The first method is called the density functional theory, or DFT. Similar to the Hartree-Fock method, DFT utilizes only one Slater determinant. However, instead of focusing on wave functions and orbitals, DFT focuses on the electron density and includes an approximation of electron correlation energy, which is the interaction between electrons in the electronic structure in a quantum system. This allows DFT to optimize the energy to a lower value and be more accurate than the Hartree-Fock. These calculations were done using the Gaussian software.
The next method we use is called multi-configurational self-consistent field method, or CASSCF. CASSCF splits orbitals into three groups: unoccupied orbitals, active orbitals with unpaired electrons, and inactive orbitals with paired electrons. This method allows electrons in active orbitals to enter other orbital groups and is computationally easier than allowing all electrons to mix between orbitals. These calculations were done using the MoleCast software. The next method we use is CASPT2. It aims to estimate the correlation energy for a CASSCF wave function using multi-configurational second-order perturbation theory. It allows one or two excited electrons from the inactive orbitals to mix between orbitals, therefore being more accurate and optimized compared to CASSCF. These calculations were also done using the MoleCast software.
Next, we move on to the results obtained from our computational methods. These are the structures of the two rhenium molecules. Unfortunately, we were unable to obtain electrostatic potential graph and IR spectra of the rhenium hexachloride 6 ion due to the fact that it has multiple ground state configurations, and DFT only considers one such later determinant. Hence, DFT calculations break the perfect octahedral structure of rhenium hexachloride 6 and is rejected. So this is the electrostatic potential graph of the rhenium 3 molecule. As expected, the more electronegative sections correspond to the chlorine atoms. And this is the IR spectra graph of the rhenium 3 molecule. From the graph, we can see that there is a huge peak at frequency of about 1300, and that most of the peaks also occur from frequencies of 1000 to 1700. And these are the 5D orbitals of the two compounds we used. The shape of these orbitals were calculated using the gradient module of MoleCast and was viewed using a software called Luskus.
These two tables compare the results of the CASSCF and CASPT2 calculations on rhenium hexachloride and the rhenium 3 molecule. These results will be used to obtain 4 ligand field parameters, which can be used to describe the properties of the molecule. The equation of the model Hamiltonian is first expanded in the basis of spin-orbit coupled state corresponding to the ground state 3T1. This matrix shows the expanded model Hamiltonian in the basis of functions. Diagonalization of this 9x9 matrix gives 9 energy states, which can be put in correspondence to ab initio states. We find the 4 ligand field parameters by fitting model states to ab initio results, by minimizing the standard deviation between the two sets of energies. We use a minimized function on the Python library SciPy. The 4 ligand field parameters are lambda, delta, epsilon, and kappa. Kappa represents the orbital reduction factor due to covalence. Lambda defines the magnitude of the spin-orbit coupling. Delta defines the axial distortion and axial splitting of the T2G shell. And epsilon defines the rhombic distortion.
These are the calculated ligand field parameters, which can be used to describe the properties of the molecule. Finally, this graph compares the measured and calculated magnetic susceptibility for the rhenium-3 molecule using CASSCF results. The 5D4 model fits the experimental data the best. This was expected as the 5D4 model includes the most number of orbitals in the active space, all 5 5D orbitals, and allows 4 electrons to mix in all of the 5 orbitals, compared to 4 and 3 of the 3T1 and T2G models. In addition to the larger active space, we also included more roots in the spin-orbit coupling. This allowed for a better description of the spin-orbit interaction. Thus, the 5D4 model represents the real molecule most accurately.
In conclusion, we have studied by ab initio computational methods 2 rhenium 3 compounds, an octahedral rhenium hexachloride 6 ion, and a neutral rhenium 3 molecule. Molecular orbitals, electrostatic potential, electronic density, low-lying electronic excited states, etc. were obtained. On the basis of the low-lying energy states, we built an effective ligand field model and evaluated the basic parameters: spin-orbit coupling, which is lambda, axial and rhombic distortion, delta and epsilon respectively, as well as the orbital reduction factor, kappa. Ab initio calculated magnetic susceptibility compares well with the measured magnetism.
Thank you.
for listening.
Thank you.